All right. This section is all about logarithmic differentiation. It's a technique, differentiation. This is a technique to find derivatives, y prime, and it could be when you have a complicated function involving a lot of multiplication, division, and raising to powers. So this technique, logarithmic differentiation, if you have a very complicated function that has a lot of multiplication and division and raising to powers, it's a way to bypass having to use the quotient rule or the product rule. The other one is when you have a function raised to another function. So you have an exponential type of function, but you have x's that appear in both the base and the powers. For examples, x to the 3x, or x plus 2 to the sine of x. It could be any kind of weird looking thing. So you have x's in this part, and you have x's up here. Notice I have x's in the base, and I have x's up in the power. So when you have a function that looks like this, the only way you can find the derivative is using logarithmic differentiation. For the first type, you can always still use the quotient rule, the product rule, the chain rule, etc. But it just simplifies. So this first lecture is just going to be on when you have a complicated function. So I'm going to start with that one. So here's an example. I have y equals 3x plus 2 to the 4th times 5x minus 7 to the 3rd power. And I want to find y prime. Now, the method that you already know is to use the product rule, where this is my u and this function is my v. So u is 3x plus 2 to the 5th, and then u prime is 5 times 3x plus 2 to the 4th times the derivative of 3x plus 2, which is 3. So you end up with 15, 3x plus 2 to the 4th, and my v is 5x minus 7 to the 3rd, and v prime is going to be 3 times 5x minus 7 squared times the derivative of 5x minus 7, which is 5. Once again, I end up with 15, 5x minus 7 squared. So then y prime is u prime v plus uv prime. So 5 times 3, you're going to have 15. 3x plus 2 to the 4th times v, which is 5x minus 7 to the 3rd, plus, and then u times v prime, you're going to have 3 times 5 once again, 15. 5x minus 7 squared times 3x plus 2 to the 5th. And then if I wanted to do some simplifying, I can factor out 2 5x minus 7s, 2 of those since I have 3 here and 2 here. And I've got 4 of those and 5 of those, and I've got a 15. So let me do a little factoring. And I will have 3x plus 2 to the fourth, 5x minus 7 squared. So if I factored out 4 of these and 2 of these and 15, all I'm left is 5x minus 7 for the first term, and then 15, and then I've got 2 of these and 4 of these, so I have just one of those left over, 3x plus 2, and I'm left with 15 times 3x plus 2 to the fourth times 5x minus 7 squared, 8x minus 5. And that's perfectly fine. There's nothing wrong with it. That's really not too bad. So there's my answer. Now, logarithmic differentiation, what you're going to do is, instead of just finding the derivative directly like this, is you are going to take the log of both sides. So you would start with natural log y is equal to natural log of 3x plus 2 to the fifth, 5x minus 7 to the third, and then you can use the rules, the property of logarithms, to rewrite the right side. So the left side is still going to be natural log of y, and then this ends up giving me 5 natural log 3x plus 2 plus 3 times 3 times natural log, 5x minus 7. And then I'm going to take the derivative of both sides. Give me a little more room. Oops. So if I take the derivative of both sides with respect to x, and I have to do this implicitly, the left side derivative, the derivative of natural log of y, is 1 over y. And then I need to make sure it's y prime because this is chain rule. Y is a function of x. And then this is actually quite easy to find the derivative. It's 5 3x plus 2, and then the derivative of 3 plus 3 5x minus 7 over 5. Looks like I'm running out of room here. And then I can multiply both sides by y. And then remembering that y is equal to 3x plus 2 to the fifth, 5x minus 7 to the third, I can replace this for y. And then distribute out. Let's see if I can do this without screwing myself up. Let's see if I can give myself a little bit of extra room here. There we go, maybe a little bit more. And if I multiply through by this, 3x plus 2 to the fifth, and I have a 3x plus 2, and you see I have a 15. And then when I multiply by this, one of these cancel with that, and I'm left with 4. 3x plus 2 to the fourth times 5x minus 7 to the third. That was dealing with the first one. Then plus 3 times 5, 15. And when I multiply by this, one of these cancel. I'm left with 3x plus 2, 3x plus 2 to the fifth, 5x minus 7 squared. I'm running out of room here. But as you can see, I'm left with exactly this thing right here. So you get the same thing. And then I can in turn simplify. So that's one example. Let me do another one. All right, so I'm just going to do straight to logarithmic differentiation. So let me go with y equals 5x squared plus 3 to the 4th times 2x minus 1 to the 5th divided by square root of 6x plus 2. Right? So it's kind of a mess. If I wanted to find the derivative, I would need to use the quotient rule first, with this is my u and this is my v. Then to find u prime, I would have to use product rule for this one. And then in turn, for its product rule, I'd have to use chain rule. And then for this one down here, I'd need to use chain rule. Doable, but extremely messy. So with logarithmic differentiation, the first thing I would want to do is take the natural log of both sides, natural log, and then I'll have 5x squared plus 3 to the 4th, 2x minus 1 to the 5th, all over. And I'm going to change this to half power, 6x plus 2 to the 1/2. Now I in turn can use the rules of logarithms to rewrite this, so I'm going to do that right here. So this is 4 natural log 5x squared plus 3 plus 5 natural log 2x minus 1 minus 1/2 natural log 6x plus 2. So remember, anything in the numerator has a plus in front of it. I can pull the powers in front, the 4 and the 5. Anything in the denominator is going to be a minus. I can pull the 1/2 in front. This is just like what we did when we were doing logarithms. But now instead of y is equal to ln, it's ln of y equals this. So I have ln y is equal to this thing right here. So then now differentiate both sides with respect to x. So the left side, you will always, always, always get 1 over y prime, always. So we're going to do d dx and d dx, both sides. And then this one's an easy one to find the derivative of. It's going to be 4, times. You have the 5x squared plus 3 in the denominator, and 10x, its derivative, in the numerator, plus 5, 2x minus 1. The derivative of 2x minus 1 is 2, minus 1/2, 6x plus 2, and its derivative is 6. And so then now multiply both sides by y. I can do a little cleaning up. So y prime, and so I'm going to have 40x all over 5x squared plus 3 plus 10 over 2x minus 1 minus 1/2 and a 6 cancels to give you a 3, so minus 3 over 6x plus 2. And then the last step is just to replace y with what it's equal to, which is this mess right here. So you'll have 5x squared plus 3 to the 4th, 2x minus 1 to the 5th, over square root 6x plus 2 times this whole mess, 40x over 5x squared plus 3 plus 10 all over 2x minus 1 minus 3 over 6x plus 2. Now if I wanted to, I could distribute this out, but you don't need to. So I would just leave it like that. And there's your answer. So it's a little messy, but it's still a lot easier than if I had done this the long way using quotient rule and then product rule for the top and then chain rule for each one of these other pieces. It just would have been really messy. So messier than this. So these are 2 examples, and I'm going to end this video and then I'll start another one showing how to do logarithmic differentiation for the other type of functions where this logarithmic differentiation is the only way to find the derivative.